So far, we've been working in electrostatics. We haven't had continuous flows of charge. We may have charge being transferred from one place to another, but usually that charge gets rearranged on the surface of a conductor in less than a microsecond, and after that, it doesn't move. Now we want to look at what happens when charges move over longer time scales or when they move continuously. We need the idea of current, which is essentially delta Q delta T. It's how many coulombs of charge move per second past a point, or through a wire, or into a capacitor, or whatever. We typically use I as the symbol for current, and 1 coulomb per second is also known as 1 ampere. A lot of times people call this an amp. This is also capitalized because it's a person's name. The name current suggests we're talking about something like water, and that is kind of a useful analogy in a lot of ways. If we have a simple circuit like a battery and a light bulb, the current flows around the circuit, and it's the same everywhere as long as the wire doesn't split. This is the way water systems work, and it's the way escalators work. If 20 people per minute get on the escalator, 20 people per minute go by the midpoint, and 20 people per minute have to get off. There's nowhere else for them to get on or get off, and people are conserved. If we want to explain why electrical conductivity works the way it does, we have to think about what's happening at the atomic level. If there's a voltage difference between 2 points in a material, the electrons want to move. We could calculate the acceleration the electron feels because we know F equals ma, and the force on a charged particle in an electric field is QE, so we could just say the acceleration is QE over m. The electron's mass is so tiny, even a very small field would give us a large acceleration. 1 Newton per coulomb, which is a very small electric field, would give us an acceleration of 100 billion meters per second squared. That might give us the idea that electrons are moving through the wires almost at the speed of light. And in fact, if we turn on a switch in a circuit and measure how long it takes the potential difference to appear across the light at the other end of the switch, we get speeds that aren't far from the speed of light, usually half, 2/3, 3/4. However, the electrons themselves are not moving anywhere close to that fast. They bounce off impurities in the metal and dislocations in the lattice of the metal, other electrons. This slows them down, knocks them backwards. And it's kind of like this game you may have seen before. If you drop discs down between these pegs, it takes them a very long time to reach the bottom because there's so much time spent in collisions. The speed of the charge carriers is known as the drift velocity, and it's much slower than the signal velocity, which turns the light on. The signal velocity being, again, a good fraction of the speed of light. A lot of other things work this way. You could hear someone unscrew the cap on a bottle of ammonia in a big room, and you'll hear it in milliseconds, but it'll take several seconds or a minute before you can smell the ammonia. If you have a garden hose in your yard and you go out and turn on the water, you may get water coming out the end very quickly, but you'll notice it's hot if this is in the summer because that water's been sitting in the sun. It'll take you a few seconds for cold water to get to the end of the hose. This is the same thing that happens with an empty hose because you're waiting on the matter to physically move there. So you can think of hoses as being like, or wires as being like hoses that are always full. We can find this drift velocity if we know a few other things. We need to know the density of free charges. Between 1 and 4 per atom. For copper, it's 1 per cubic meter, and we use a little n to indicate this. So it's a constant for each metal. The charge on each carrier, which is just the electron's charge, the total current, and the cross-sectional area A of the conductor. So pi r squared for the size of the wire you're using. Our formula for this drift velocity is I over nqa. What are typical velocities of drift, or typical drift velocities for conductors? Well, one thing we have to ignore is in your house, the electrons are really going back and forth 120 times a second. They change direction. If we ignore that and pretend your house is run on batteries, that are equal size instead. Let's say you have a high current appliance like a hairdryer plugged into an outlet with 14 gauge wire, which is pretty much normal setup for a house. We can look in Wikipedia and see that the area of that wire is 2.08 square millimeters. Notice that's 2.08 times 10 to the negative 6 square meters. The current I should be about 15 amps, and our value of N for copper is 8.3 times 10 to the 28 per cubic meter. We put in all the numbers, do the math, and we get 0.00054 meters per second. That's half a millimeter per second. If we go out to your car, when your car is starting, your battery cables are probably 4 gauge, meaning an area of 2.1 times 10 to the negative 5 square meters. If we have a large engine we're trying to start in winter, the current could be several hundred amps. This will give us a large current per area, and therefore we'll get a higher drift velocity. So if we put in these numbers, notice the charge and the free electrons in copper haven't changed, we get 2.5 centimeters or 2.5 millimeters per second. So faster than before, but still 2.5 millimeters in a second is ridiculously slow. If you look up the speed of a garden snail, according to Google, it's traveling 5 times that fast. So the speed for the charge carriers is interesting, but what's more important is connecting the voltage across something and the current through it. We call this equation that connects these things Ohm's law, and we write it as V equals IR. This is the most important equation when you're talking about wiring something. Voltage and current mean what we've taken them to mean before. The new part here is R. This represents how hard or easy it is for charges to move through an object, and this is called resistance. Units of resistance are ohms, and again, that's someone's name, and the symbol is the Greek capital omega. So just like we can buy capacitors with a certain ability to separate and store charge, or capacitance, we can buy resistors which have a certain ability to slow the flow of electricity. According to Ohm's law, if we put a potential difference of 1 volt between the ends of a 1 ohm resistor, we'll have a current of 1 amp flowing in that resistor. Now, not all materials obey this V equals IR expression, and it turns out it's because this isn't really Ohm's law. There is a law, which means it works for everything by the same name, and it's a little bit different, but that Ohm's law reduces to this thing, which is very commonly correct in certain circumstances, and this is what everybody on Earth means when they talk about Ohm's law in almost every case. Things like the LEDs in lights and even the old lights that got hot, the incandescent light bulbs, they don't really follow this law very well. If we want to look at what resistors look like, these are things that are made specifically to satisfy Ohm's law. We want them to work like this so that V equals IR. And you can see there's a whole bunch of different sizes. The resistance is not determined by the size, but the amount of power that can be dissipated is determined by the size. These smallest ones are 1/8 of a watt all the way up to these 20 watt, and you can get much bigger.